Consider a particle that is moving within a curve and has a velocity v. The direction of the velocity vector here is not just a random direction. It is always tangent to the curve. But how do we know the direction of the tangent in this case? Basically, if a particle is moving within a curve, then for each segment of its motion, it has a center of rotation. And this is the concept which defines the normal and tangential coordinates, where S is the displacement along the path, UN is the normal unit vector which points towards the center of the curvature, and UT by default is the perpendicular to the normal. Therefore, we usually find out where is the tangent by locating the normal first. So the velocity vector is defined by its magnitude and tangential direction, with the magnitude defined by the change of displacement with respect to time, or ds over dt. Within each segment of motion in a curve, ds is defined by the radius of curvature ρ and the incremental angle corresponding to that segment, which is d theta. And notice also here that the radius of curvature is not constant if the curve is not uniform, since it depends on the concavity. Remember this? Well, this is a uniform closed curve with the radius of curvature equals r. And in this case, S is always defined by r times theta. And that's why they told you in math that the circumference of a circle is 2 pi times r. It's basically r times theta over the whole circle now, which is 2 pi. How about the acceleration of a particle moving in normal and tangential coordinates? Simply, it has a tangential and normal acceleration components that define the total acceleration vector, which is made of the magnitude and direction of both components. The tangential acceleration is defined as the change of velocity with respect to time, and this is clear from the definition of the velocity, which is always tangent to the curve. Note also that we can find at from the second derivative of s with respect to time. On the other hand, the normal acceleration is defined as v squared over ρ, and it is directed towards the positive direction of the normal coordinate. Finally, the magnitude of the acceleration is defined as the square root of at squared plus an squared. But what happens to the acceleration if the velocity is constant? In this case, v does not change by changing time, which means that at equals to 0, and an becomes now the total acceleration of the particle, and the total acceleration direction now is in the positive normal direction. Okay, let's clarify something together. Consider a segment in a curve for which the radius of curvature is defined as ρ. This is what we know so far, where at and an are defined. But what if the motion of the particle happens in a straight line instead of a curve? Well, unlike the curve where the tangent changes its direction, in the straight line, the tangent is always along the line, which means the normal direction is always vertical, and we don't have any finite meeting point like this one, and therefore the radius of curvature exists only at infinity. This means an now becomes equal to 0 because of ρ at the denominator, and this brings us to the motion that we already know in a straight line, where a is equal to dv over dt. The bottom line is an exists only in curves. No curve, a equals dv over dt. And similar to what we did in previous lessons, we can eliminate time from v and at to find the relation at ds equals v dv. And if at is constant, our three constant acceleration equations apply as usual. Note that everything here is applicable only in the tangential direction. Finally, if this type of curvilinear motion is defined by a function such as y equals f of x, The radius of curvature is mathematically defined by this relationship, for which the first and second derivatives of the curve need to be found at some given point x and y. Okay, let's take an example. The driver of a car applied brakes to produce a uniform deceleration. The speed is 90 kilometers per hour at the bottom A and 36 kilometers per hour at the top C, which is 150 meters along the road from A. If the total acceleration at A is 3 meters per second square and rho at C is 100 meters, calculate A, the radius of curvature at A. Okay, so what is given in the problem so far? The velocity of A, which needs to be converted to meters per second, so we multiply it by 1000 and divide it by 3600. Or basically, divide by 3.6 as we do here for VC. Now, the radius of curvature at A can only be found if the normal acceleration at A is known. And since VA is given, our goal is to find AN at point A so that we can solve for rho A. And since the total acceleration at A is given, and from the definition of total acceleration, if we need to find AN, we need to first find AT, and then solve for the remaining unknown here, which is AN. So our goal now is to find the tangential acceleration at A, which can be found for the whole distance using the constant acceleration equation between C and A. We know both velocities, and we know also the distance. Solve for AT, which happens to be negative because of the deceleration. Using AT in the total acceleration at point A and squaring both sides, our unknown AN is easily found to be 2.44 meters per second square. And this is what is actually happening. AT is negative, AN is positive, and A will have this direction. And rho now can be found to be 256 meters. Part B is asking for the acceleration at the inflection point B. And at the inflection point, which is the point between the two curves, the motion is in a straight line and we only count for the tangential acceleration here. And the question also asks for the total acceleration at C. So for the acceleration at point B, the acceleration is only tangential, which is constant between A and C, and already found to be minus 1.75 meters per second square. And to find the total acceleration at C, we need to find AN first, which is V square over rho, and it's equal to 1 meter per second square. So the total acceleration at C by definition becomes 2.02 meter per second square. And note that the tangential acceleration is valid all over the path from A to C. And what makes the total acceleration changes at each point is AN. So at A, AN was found to be 2.44. At B, there is no AN. And at C, it also has a different value. The direction of AT is opposite to the positive tangent. AN is positive towards the radius of curvature. And A at C will have this direction.